Hello dear student, this is from Engg Institute of Engineering and Technology. We are learning the subject Basic Electrical Engineering, and in our last session we have discussed about following topics: three-phase induction motor. So today we are going to discuss about a rotating magnetic field. That is the main principle behind the three-phase induction motor. After that we will discuss about single-phase induction motor, DC machine and alternator. So let us start and discuss with the rotating magnetic field. We will discuss about the rotating magnetic field of three-phase induction motor. What is the principle behind this rotating magnetic field? Before discussing the principle, we will check the arrangement of rotor winding in three-phase induction motor. And here, three-phase windings are placed 120 degree apart with each other, having the currents displaced in time 120 degree and magnetic flux produced with the rotates in a space. So here you can see the rotating magnetic field here will be produced. So once you apply the three-phase AC signal, see this particular winding will produce a rotating magnetic field which is 120 degree apart with each other, where the stator of three-phase induction motor carries the three-phase star or delta connected, which are displaced from each other 120 degree in electrical way. So from that we are applying the three-phase AC signals in form of current IR, IY and IB. So once you apply this three-phase currents, that will produce a magnetic flux in winding. So produced magnetic flux are also phi R, phi Y and phi B. All are produced which are displaced by 120 degree apart with each other. So as we already know, the equations of flux is like phi R will start with the angle 0. So we define as here phi R is equal to phi m sine omega t. Phi Y, which is 120 degree apart from the red flux. So here we define as phi Y is equal to phi m into sine omega t minus 120. Likewise, we define phi B is equal to phi m sine omega t minus 240. Right. So here all these three flux are nothing but 120 degree apart with each other in this particular vicinity. Where if you draw the phasor diagram, you can see this all these three fluxes are in 120 degree apart with each other, where you can see here where all this three-phase current produces the own flux which is sinusoidal and which can be represented as like this way, where all these three equations you can represent like phi r is equal to the maximum value is phi m. So phi r is equal to phi m sine omega t. After 120 degree there is a production of phi y, and after 240 degree there is a production of phi b. So in terms of the waveform you can represent all this mathematical equation here is nothing but the production of magnetic flux in three-phase induction motor. Now all the fluxes are being produced at different angle. One is at the 0, another is at minus 120, third is at minus 240. So during this process, if we find the magnetic flux movement in this three-phase induction motor, you can check like this way. So we can take here three instances, like one of the instant we'll take at angle 0, another at 60, one is at 120 and finally it's 180. So if we take the instances, let's say our equations are here where I am going to take omega t is equal to 0. So I am going to take here this value is equal to 0. So once I am going to put this as the vector or flux starts at angle 0. So from this you can be able to see phi r is equal to phi m sine 0, it becomes 0. Same way phi y is equal to phi m sine minus 120. So this will be a minus phi m, that is equal to 0.866 into phi m. Phi b likewise you will find a positive 0.8666 into phi m. Now this three fluxes, if you are going to put in a phasor diagram, you can find here the total flux phi t is nothing but the summation of phi r plus phi y plus phi b. So in that we'll take the phasor sum of all this, and we'll find here phi t is equal to 2 into 0.866 phi m into cos 60 by 2 from this diagram. So you can see from this phasor diagram, once you apply this trigonometry here, the total flux at this particular position where omega t is equal to 0 is 1.5 times of the maximum flux value. So here phi t is equal to 1.5 into phi m. So that can be represented as here which is 60 by 2. So this is what the resultant value. Now you can check this position of this phasor diagram. Now we take the second instance as omega t is equal to angle 60, where you can see once you are going to take a 60 and put it all in these equations, you will find the 5t that is equal to same as 1.5 times of phi m. So but this position is quite different, where you can see from the initial position where omega t is equal to 0, this position is like this way. Then after that, the at angle 60, you can see there is a complete phasor diagram is move upward direction, right? So here what we are proving that how the magnetic flux that is going to be rotated in three-phase induction motor. So by this way, you can see the magnitude of the production of flux being same, but the position of this phasor diagram, the position of this vectors or position of this magnetic field is now continuously rotating. So at omega t is equal to 60, see this is slightly rotation in this direction, in a clockwise direction. Resultant flux has rotated clockwise through an angle of 60 from the position at instant 0. Right now, if you take the third instance at omega t is equal to 120 degree, and once you find the phi t, and that is equal to, again the magnitude is same, but see the position of this magnetic flux or magnetic field is again rotating in a clockwise direction. So at all the instances at 0, 60 and 120, you can check from this phasor diagram is continuously in a rotation. So here resultant flux has rotated clockwise through an angle of 120 from the position of instant 0. So here you can check this particular magnetic flux is going to be rotated at different instances at 0, 60, 120, 180 and so on. So from that you can prove this this particular magnetic flux is nothing but, this particular magnetic field is nothing but the rotating magnetic field. Now this is what the important phenomena of three-phase induction motor. As from this discussion it is clear, the resultant of three alternating fluxes separated from each other by 120 degree has a rotating field of constant amplitude of 1.5 times of phi m moving around the machine periphery. So the speed of rotation of that magnetic field is nothing but, which is magnetic field rotates, is called the synchronous speed. So whatever speed this magnetic field is rotating, that speed we define as a synchronous speed. So here the speed of rotating magnetic field we define as a synchronous speed. So from this you can find the synchronous speed, ns is equal to 120 times of frequency multiplied by number of poles. So here f stands for the frequency and p is nothing but the number of poles. Right now we can discuss here the principle of rotating magnetic field. So once here the magnetic field is being rotated, that means the rotor is now going to follow the speed of rotating magnetic field. So here rotor speed is now trying to catch the speed of or the synchronous speed of the rotating magnetic field. Now how this can be possible? Just let us understand this phenomena where the outer portion, you can check here, this is nothing but the rotation of the starter field. Now this is the starter, so this portion is the starter, inside this is a rotor conductor. Right now, as such, this starter, when you apply the three-phase signals, this starter will produce a rotating magnetic field, and with this is a small air gap between a stator and rotor. So with this phenomena, the rotor is also going to follow, is also going to rotate and follow the direction of rotating magnetic field. By that way, here the electrical signal is converted into a mechanical signal. So here you can see the three-phase stator winding is energized from three-phase supply, and a rotating magnetic field is produced which rotates at the synchronous speed of ns, where the rotating field sweeps the air gap between stator and rotor and cuts the stationary rotor conductors. So from this you can say that the EMF is induced in a rotor conductor due to the relative speed between the rotating field and stationary rotor. So as the rotor is short circuited, current will flow in the rotor conductor. So here the current carrying conductors are placed in the rotating magnetic field produced by the stator. So from this you can see that a mechanical force is found to be acting on the rotor conductor. So here from this phenomena where the mechanical force is being generated, because this particular stator is having the rotating magnetic field, and this rotor phenomena you can see here where current flows in this particular rotor. So due to this there is a force is being exerted as per the opposite direction of these two magnetic poles. So because of this there is a repulsion of this stator rotating magnetic field and this rotor, where it will generate a force, and that force we define as a force on a rotor conductor, and that will give the rotor come in a rotational condition. So here the sum of mechanical forces acting on all the rotor conductor produces a torque which tends to move the rotor in the same direction as stator rotating field. So here all conductors are carrying the current, and because of this carrying the current, each conductor will exert a force, and that bunch of force we define as a part of the torque. So that initial torque will be generated through these mechanical forces. So from this you can say the direction of rotor rotational in the same direction as the stator can be explained by Lenz's law. So because of this the induced current and induced flux act in such direction so as to oppose the very cause of that production. So the cause of production of rotor current is a relatively speed between the rotating magnetic field and stationary rotor conductor. So to reduce this relative speed, the rotor runs at the same direction as the stator tries to reach it here. So ultimately here rotor is going to follow the speed of rotating magnetic field and is never going to attain. Once it's going to attain, again the flux it becomes zero. So this never going to be happen. So in this three-phase induction motor, always remember the speed of a synchronous speed ns is always greater than the speed of rotor. So here the speed of rotating magnetic field is always greater than the speed of rotor, right? Thank you dear students. If you have find any difficulty, please write in the comment box. Thank you very much.